Hello, and welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the figures that count in the history of mathematics. I'm Benjamin Cornish, and today's episode is about a man with curves in all the right places, Apollonius of Perga. I used to have a friend who was a thief. That's not a metaphor or a comment on someone's moral outlook. He literally stole things. Sacks of grain, bolts of cloth, the occasional cartwheel. Not the cart, just the wheel. He said it created enough inconvenience for the rich to count as economic redistribution. He wasn't very stealthy, mind you. He stood out with a very distinctive green coat and a hat. Well, it was more of a hood. He used it to cover his face, thinking that it would hide his identity, but given he was the only person in the forest to wear such a hood, that actually became his nickname. But the thing about this friend, let's call him Rob, was he was kind of a genius. Not in the proof of Fermat's last theorem sense, more in the unexpected excellence with a crossbow while balancing on a wooden fence sense. It was uncanny. He could hit an apple on a barrel from across a clearing, with just enough of a parabolic arc that you'd think he'd pre-computed it. I once asked him how he aimed. He says, think like a conic. You don't fire at the apple, you fire through it, as if it were a focus and your aim with a directrix. Which, I'll admit, was a baffling answer from someone who couldn't spell ellipse, but he had an intuitive sense of trajectories that would have impressed Apollonius himself. Rob's arrows curved through space with such elegant inevitability that you felt bad for the targets. It was like witnessing a representation of light bending around the gravitational field of a larger planet. He used to say that he only stole to feed the neighbourhood. He wasn't interested in status or castles or anything that involved a feudal hierarchy. He just wanted to redistribute wealth with a bit of flair and a decent shot grouping. In modern terms, he was a one-man fiscal policy with a strong projectile analysis. Anyway, one day the local mayor announced a grand archery tournament. And of course, Rob couldn't resist. It was invitation only, very exclusive, velvet ropes, custom arrows, that sort of thing, and I told him it was a terrible idea. Entering a competition run by the people who wanted him locked up? Oh dear. He said, Ben, it's not about the money, it's about reminding people that geometry can humiliate the powerful. Which was fair enough. He turned up, in disguise, one of those very convincing peasant cloaks, and stood in line like the rest of them. When his turn came, he loosed an arrow so clean, so mathematically pure, that it split another arrow down the middle. Classic trick shot. The crowd went hyperbolic. The mayor fumed. Someone fainted. And Rob disappeared before the prize ceremony, leaving behind a bag of winnings that somehow turned into flour and candles for his entire neighbourhood. No one knows how. I'll tell you this, partly because it's the best real-world example of applied conics I've ever seen, but mostly because Rob was thinking in curves, while the rest of us were worrying about straight lines, rules, roads, obligations. He was aiming through ellipses, seeing the full arc, letting geometry tell the story. And today's mathematician, he thought in curves too. Apollonius of Perga traced the path that Rob's arrows would follow, centuries before they were launched. He gave us the language to describe them, the equations to model them, and the names that stuck. Ellipse, parabola, hyperbola. He saw shapes not as ornament, but as consequent. The kind of shape that tells you not just where something is, but how it's travelling, what it's becoming, and where it's about to end up. So, in honour of Rob and his slightly illegal use of conics, let's talk about the man who charted their course. Now, before you start confusing him with other Apolloniuses, Apollonius of Tyana, the mystic philosopher, or Apollonius of Rhodes, the poet with thing for Argonauts, let's set the record straight. We're talking about Apollonius of Perga, who lived in the 3rd century BCE, probably between 240 and 190 BCE. He was born in Perga, a city which is now southern Turkey, during a time when the intellectual afterglow of Alexandria was still lighting up the Mediterranean. We don't know much about his personal life. Historians suspect he studied in Alexandria, perhaps under the successors of Euclid himself, and that would make him something like a mathematical grandson of Euclid. What we do know is that Apollonius had an obsession with curves, especially conics, and he wasn't afraid to push a good parabola when he saw one. He wrote extensively, and his most significant work, Conics, originally spanned 8 books. Only the first 4 survive in Greek, the next 3 come to us in Arabic translations, and the 8th is lost entirely. But before we get conical, I might leave that pun, let's talk about what else he got up to. Apollonius lived during the Hellenistic period, a time where the Greek thought had spread across Egypt, the Levant, and as far as modern-day Afghanistan, thanks to Alexander the Great's very ambitious gap year. Apollonius worked within this bubbling stew of scholarship, correspondence with peers in Pergamon and Alexandria. His letters are often preserved in the prefaces to his books. He had a strong interest in astronomy, attempting to mathematically model planetary motion. But then, who didn't? His tools of choice? Epicycles, deference, and a healthy distrust of overly simplistic circles. His astronomical work drew a circle that Ptolemy, especially in the Almagest, would later build on with another circle, centred at the rotating point of the first circle. In a world still getting used to the idea of heliocentrism, Apollonius was already fiddling with the geometry of orbits. He proposed models of planetary paths, relied on nested circular motion, complex systems that matched observed data while maintaining a geometer's sense of elegance. His ideas would echo through the ages, all the way to Copernicus, Kepler, and Newton. So yes, Apollonius wasn't just the curve guy, he was also a bridge between geometry and astronomy, a celestial architect with a very, very big compass. Let's talk about what Apollonius is best remembered for, his work on conic sections. These are the curves you get when you slice a cone with a plane at different angles. Think of it as artisanal cone slicing, geometry for those with refined taste. His idea wasn't new. Menaechmus, a student of Plato, had discovered conics in the 4th century BCE, that's episode 14 for those paying attention, while trying to solve the cube duplication problem. But Apollonius was the one who took conics from a curious curiosity to a fully fledged mathematical discipline. In his work, Conics, he not only gave us the names Ellipse, Parabola, and Hyperbola, but also introduced a systematic approach to studying their properties. Before him, the names didn't exist. Now they're the bread and butter of coordinate geometry, calculus, orbital mechanics, and even the occasional roller coaster design gone wrong. Let's start with the basics. A cone is a surface generated by a line, the generator, rotating around a fixed axis, the axis, intersecting the axis at a point, the vertex, and sweeping out a circular path, the base. Notice that this would actually create 2 cones, given that the generating line will exist on both sides of the vertex. When you slice the cone parallel to the base, you get a circle. When you slice the cone at an angle to the base that is not steep enough to intersect the base, you get an ellipse. When you slice the cone at an angle that is exactly the same as the angle of the side of the cone, you get a parabola. And any steeper than that, the plane intersects both napes of the cone, that is, the top and the bottom, either side of the vertex, and that gives you a hyperbola. Apollonius didn't use the coordinate geometry. The Cartesian plane wouldn't be invented for another 1800 years. In fact, he predated Descartes with his own coordinate system. This measured the distance along a diameter of a conic and the distance along the tangent to the conic at the point of the diameter. Here, we might run into difficulty, because the diameter can be defined as any point that passes through the vertex of the conic, which, for the case of the hyperbola, doesn't necessarily pass through the conic at all. In order to construct this, we might begin by cutting a plane through the vertex of the original cone, such that it is collinear with the axis of rotation, and for a circle this would yield a diameter. For the other conics, it's a little more fun. The tangent, then, would be defined in the normal way of a tangent, and these pairs of lines would not necessarily be perpendicular. Only in the case of the circle are they necessarily perpendicular, but they are still always linearly independent, thus will suffice as a coordinate system. Now, you might feel that this is an unwieldy definition, in that it is variable and unique to the conic. But whilst it lacks the simplicity of Descartes' orthogonals, it produces the beauty of ancient Greek maths. The concept of a diameter of a cone may also be defined as the line that bisects all chords parallel to a given direction, and this anticipates the modern idea of conjugate diameters and tangents. It's also a key concept in projective geometry, which wouldn't emerge formally until the 17th century. As I say, it's beautiful. One of the mind-bending aspects of Apollonius's work that he evidently did algebra without algebraic symbols. No x, no y, no equal sign, no expressions to rearrange, just diagrams, words and lines. His propositions resemble Euclid's, but the techniques go deeper. Apollonius introduced ideas equivalent to quadratic equations, tangents, normals and loci. He compared segments, ratios of areas, and the squares of lengths, effectively anticipating analytic geometry by almost 2 millennia. For example, the parabola, as defined by Apollonius, has a property equivalent to y squared equals 4ax. Now, he didn't write this, but his geometric constructions imply it. He studied the relationship between points, directrices, and focal properties long before these terms entered the mathematical vocabulary, and this makes reading Apollonius both frustrating and awe-inspiring. It's like trying to read the instructions to set up a new printer written in Elizabethan English and illustrated with spaghetti. He also worked on curvature in a rudimentary way. His studies of tangents and normals to conic sections touch on the modern idea of a curve's bending, though the formal concept of curvature would wait for Leibniz and Euler. Still, Apollonius understood that the shape of a curve affected how it intersected lines and other curves. He laid the tracks for differential geometry long before it ever caught a train. Now that we've admired Apollonius's curve catalogue, let's focus on a particular challenge he set geometry, a puzzle that would keep mathematicians busy for over 2,000 years. It's known today as the Apollonius Problem. The problem asks, given 3 objects, each one either a circle, a point, which is like a circle with 0 radius, or a straight line, which is a circle with infinite radius, if you're feeling so bold. Can you construct a circle that is tangent to all 3? Sounds simple. It's not. This is classic geometry's version of a bar bet. 3 shapes walk into a plane and Apollonius has to draw a circle around all of them. The general version, with 3 given circles, can have up to 8 different solutions. That's right, depending on whether the solution circle is internally or externally tangent to each of the 3 given circles, there are 2 times 2 times 2, 8 possible combinations. And unlike most conic work, this problem can't be reduced to simply bisecting lines or drawing perpendiculars. Solving it geometrically requires clever constructions, often using inversion, a technique that Apollonius probably didn't have, but which later geometers developed, possibly inspired by the problem itself. Apollonius's original method for the problem are lost, which has sparked centuries of mathematical fan fiction. Pappus of Alexandria, writing about 400 years later, attributes the problem of Apollonius, but doesn't say how he solved it. Later solutions came from giants like Vieta, Descartes and Newton. In fact, Descartes took the problem into coordinate form, giving us the famous result now called the Descartes circle theorem. It provides a formula relating the radii of 4 mutually tangent circles. That is, k4 is equal to k1 plus k2 plus k3 plus or minus 2 lots of the square root of k1 k2 plus k1 k3 plus k2 k3. And here k refers to the curvature, and that is the reciprocal radius for each circle. There's also an algebraic way to approach the problem, using Mobius transformations and complex numbers. These methods belong to the mathematical toolbox of the 19th and 20th century, but they show just how deep a single classical problem can go when tossed into the modern blender. The Apollonius problem remains relevant in fields like robotics, motion planning and computer graphics, anywhere you want smooth navigation between obstacles. So even though it was born in a world of parchment and compasses, It now lives in silicon. So the next time you push 3 coins together, know that you're reenacting one of geometry's oldest thrillers. Apollonius saw the tension in circles, and then solved it with a compass and excessive confidence in tangency. The puzzle has also been generalised endlessly. There are versions in 3 dimensions, spheres tangents to other spheres, versions in hyperbolic space, and even versions in taxicab geometry, where circles look more like diamonds. In 3D, the question becomes, given 4 spheres, or combinations of spheres, points and planes, how many distinct spheres exist that are tangent to all 4? Turns out, the answer is not 8 anymore, but up to 16. This is because the number of configurations increases significantly when you add a dimension. Spheres can wrap and interleave in more complex ways than circles ever could. It's like trying to juggle 4 soap bubbles inside a box, except now the soap bubbles can hide behind each other and whisper mean things about your geometry skills. This version of the problem is sometimes called the spherical Apollonius problem. The algebra behind it gets wild quickly. Quartic equations, multivariable systems, and constraints that make even seasoned algebraists consider early retirement. But it doesn't stop there. In n dimensions, the generalization asks for a hypersphere tangent to n plus 1 given n spheres. That is, in 4 dimensions, you'd be solving for a 3-sphere, which is the 4D analogue of a sphere, tangent to 5 other 3 spheres. The number of solutions grows, and the geometric intuition shrinks, just like my confidence on the first lecture of Introduction to Topology. Even though we can't see 4-dimensional space, we can still describe it algebraically, using tools from algebraic geometry. We can formulate the constraints as systems of quadratic equations. The resulting hyperspheres exist, in the same way complex numbers exist. Not visible, but very real in terms of satisfying the equations. In computational geometry, there's a related structure called the Apollonius diagram, a variant of the Voronoi diagram, but where regions are defined by proximity to circles, or spheres, instead of points. These diagrams are vital in mesh generation, path planning, and all sorts of geometric reasoning under constraints. So, Apollonius's 3-circle riddle didn't just echo through classical geometry. It grew legs, climbed dimensions, and is now haunting machine learning engineers who just wanted their algorithm to run faster. You might be wondering, why care so much about conics? And the answer is because so does nature, especially gravity. When Newton later formulated his laws of universal gravitation, he realised that celestial orbits must be conic sections. A planet, under the influence of an inverse square force, traces an ellipse, or if you're unlucky, a hyperbola. The Principia, which we will cover in the Newton episode in about 30 years' time, uses conic sections extensively, and those concepts were built atop the apex of Apollonius's work. And this is not me being hyperbolic. In Book 1 of the Principia, Newton used results from Apollonius to handle the geometry of orbits. And that's like writing a biology paper today and citing Aristotle. Not quite peer-reviewed, but undeniably peerless. Apollonius also explored epicyclic motion, the idea that planets move in small circles whose centres themselves move along larger circles. This model aimed to reconcile observed retrograde motion with the idea of perfect circular orbits. While we now know planetary motion is elliptical, not epicyclic, Apollonius's geometric models were critical stepping stones. They represent one of the first efforts to mathematically model complex physical phenomena. And let's not forget Apollonius's cutting-edge work on normals and tangents to conics. These concepts would later become central in physics for understanding motion along curved paths, optics, and even general relativity. In particular, I would propose the idea of velocity, which is always measured in a linear way as the derivative of displacement, where the displacement is perhaps an elliptical orbit, and the velocity is therefore a tangent to this orbit. For me, this hints at the notion of differential calculus, long before the idea of a derivative was around. As it happens, I have recently found myself in an argument on Reddit about who invented calculus, so it's been on my mind recently, the idea that everything is built on everything else. So while Apollonius didn't have Newton's laws, he had something better, an intuitive grasp of curves that really bent the rules. Despite all this, much of Apollonius's work has been lost or only survives in translation. The 8th book of Conics is gone, and with it some of his most advanced insights. Who knows, perhaps it was book 8 where he more formally introduced the partial differential equation. Other lost work include On Cutting of a Ratio, On Determinate Sections, On Contacts. These sound like either esoteric geometry text or very niche dating guides. We can assume they contained advanced geometric constructions involving multiple conics, problems about finding points tangent to several curves simultaneously, and what we would now classify as systems of quadratic constraints. Some historians argue that these constructions anticipated modern algebraic geometry and optimization theory. So we aren't just missing his notes, we're missing entire chapters of the history of maths. Yet, even in absence, Apollonius's impact is visible. Projective geometry, developed centuries later by Desargues and Pascal, echoes with his ideas. The concept that a conic is defined by 5 points, well, that's Apollonius in disguise. The use of duality in geometry, again, his fingerprints are all over it, like a mathematician caught red-handed with a protractor. In modern terms, conics are the first non-linear curves we teach. They bridge linear algebra, calculus, and geometry. They appear in algorithms, physics, simulations, astronomy, architecture, and computer graphics. And their properties, focus, eccentricity, directrices, they owe a massive debt to the man from Perga. Apollonius of Perga was many things. A geometer, an astronaut, a theorist, someone better than me at editing text, and whether he knew it or not, a precursor to modern maths. He redefined what it meant to describe a curve. His writings went further than previous geometers, offering general methods and classifications that elevated conics from isolated curiosities into a field of study. And he did it all with no algebra, no graph paper, and no XYZ coordinates. In many ways, he is the last great geometer, before algebra took over the mathematical world. His work represents the apex of the classical synthetic style, a style that would go underground for centuries, only to be reawakened by the likes of Descartes and Newton. But don't fear, we still have a few lesser lights to discover in the world of Greek geometry, although none shone so bright. Coming up over the horizon, we are yet to meet Heron, Ptolemy, Pappus, and a few others. But you might notice that the podcast is beginning to shift gears, back into number theory, and even more excitingly, into early algebra. The Greeks are dying, and the Romans, well, they aren't actually all that bright, and they are a little bit too preoccupied with engineering to do any proper maths, which means the next few hundred years are going to race by. And before we know it, we're going to be smack into the start of the Islamic Golden Age. And if you can't wait for all of that, then you can listen to some of my musings in between episodes on Blue Sky, where occasionally I post interesting things that I'm researching ahead of these podcasts. You can follow me at mathematicians-pod, and I'd be happy to chat to you there. Until then, though, thanks for listening to the Mathematicians Podcast. I'm Benjamin Cornish. Join me next time, where I will be bringing donuts to share, as we get a little more topological than I'm comfortable with. A high-spirited podcast, yes, you heard that right, on Perseus. Until then, goodbye. The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.